now you know who that was. Kris will tell us about cumulative Euler flows. And if you do have a question during the talk or after the talk, let me know, because I have to give you the microphone. So Kris, thanks again for speaking virtually. Take it away.
Thank you. Thank you for the invitation, the organizing committee. And I'm very happy for the flexibility. I should have been there, but I'm still waiting for my green card renewal. So I'm going to talk about cumulative Euler flows. And I wanted to start with a quote that I found amusing in an obituary of Jacob Schwartz, or his obituary. It was written by Peter Lax. Before I show it to you, I wanted to give you the context. Apparently, Jacob Schwartz, who is half of Dunford and Schwartz, wanted to teach. He had the goal of teaching every math class at New York University. And so here is the quote. Peter Lax asked him if there was a subject he had trouble learning. And he admitted, namely fluid dynamics. And he told him that it's not a subject and can be expressed in terms of theorems and their proofs. So on that happy note, I'll start talking about fluid dynamics. I found it amusing. So this is from an obituary. Okay. The outline, let me first give a quick outline. I'll only be talking about the Euler system, and the goal is to seek singular radial solutions. In also one-dimensional solutions are of interest, and we'll get back to that. I'll review some results on self-similar amplitude blow-up, some things I worked on and something. It's very active, so there are many, many, many results. I will not have time to cover all of it. But the main reason, or the main interest in this talk is the question if something worse can occur, and in particular, if accumulation can occur. I'll define we can define it right away. Accumulation in this talk will mean that a delta, the direct delta, occurs in the density field. So mass accumulates. There are other types of accumulation one could talk about, but here it's mass. And it's easy to give examples of this, but these are kind of trivial cold gas examples. I will quickly go through that. I'll spend more time on, this is again a well-known class of solutions, and they are what some people refer to as affine flows, and it's been around for a long time. But we'll look at them and see what they have to say about accumulation. And I'll have a summary and some next issues. So here is the full compressible Euler system that we all love. And there isn't much to say on this page, except that everything I say is about an ideal polytropic gas. And there is it's the pure Euler system. There is no external force field, no self-gravitation, just this. Okay, so it's Euler alone. And it's ideal and polytropic, as I said. So that's impossible to solve. So we reduce to radial flows. Also, if you're interested in singular phenomena, that's a good place to look. So the notation is R is the radius. We are in 1, 2, or 3 space dimensions. And I abuse notation a little bit by not changing the name of the variables. They are now functions of time and radius only. And the velocity field is radially directed. So the motions are in some sense trivial. They are along straight line, every particle along a straight line through the origin. So if you rewrite the Euler system, and shocks will not play any role in this talk, so everything is smooth. So you can rewrite the Euler system for rho, u, and c being the sound speed. And it takes this form, and in higher dimension 2 or 3, you notice that you have geometrically singular source terms. So you would expect, it's very natural to expect that you can produce amplitude blow up via wave focusing. And this is old news. I apologize for those people who know all this better than me, but let me say it anyway. So that, of course, this system is by no means trivial to solve. There is no result currently known, even for this case. We're talking about the full Euler system that gives you global in time existence, say, of weak solutions or even non-weak or classical solutions. There is no Glim theorem in this setting that is known. So it's challenging. And so it's very natural to look for self-similar solutions. So this field I think, is cursed by two curses. One is that papers are 200 or 300 pages long by now. That's just how it has to be if you want all the details. And the other curse is more notational. Nobody seems to agree how to write the similarity variables and the similarity parameters. So I'm going to stick with what's in, I guess it goes back to Courant Friedrichs at least, and also in Lazarus' comprehensive work. So here is the notation I'll use. X will denote the similarity variable, which I take to be time over R to lambda. And lambda is a parameter you're free to choose. With this choice, it makes it a little bit easier maybe to do global in time solutions. So of course, time zero is going to play a special role. That's when collapse happens in these solutions. You could translate that in time, but we put it at time zero. With the setup, so it's good to keep in mind that the sign of the similarity variable and the time variable are always the same. And okay, so the Euler system standard derivation shows that it admits self-similar solutions of the following form for rho, u, and c. I'm leaving out some signs and some constants in these expressions that are not important for now. But there are two similarity parameters, lambda and kappa, and lambda appears for u and c, and kappa for the density. So one can notice that in this way of writing it, the capital V and the capital C, so the self-similar dependent variables V and C, are non-dimensionalized velocities or speeds, so they are on the same footing. But a priori, before we do anything with this, the kappa and the lambda are free parameters. Of course, for concrete cases, if you impose certain physical restrictions, such as finite, locally at least, locally finite mass, momentum, energy, there will be restrictions on these parameters. If you think about the physical setup, it's very simple. As I said, particles are moving in straight radial lines through the origin, but the whole setup has four parameters: space dimension, n, what gas are you looking at, gamma, and then the two similarity variables. So it's surprisingly, maybe not surprisingly, it's very rich. There are many things that can be exposed in these type of solutions. So here I've drawn the situation in the physical plane, in the RT plane. This is for lambda greater than 1. And these curves, these bold curves, are x curves, where x remains constant. So we are interested in solutions for, well, ideally for all times, but at least up to time of collapse, time zero. And I should point, if you're not used to these equations, do not think that these are particle trajectories. They are not, okay? They are just where the self-similar variable x is constant. So, okay, so that's important to keep in mind. Here I've just rewritten the variables in similarity form. Now, it's a fact that I'm not going to go into, but let me describe it quickly, that if you build a solution like this with a well-defined solution at time zero, the fractions v over x and c over x must necessarily be finite numbers, okay? So that you get the well-defined flow field at time zero. And that will be the case in the solutions that we discuss, okay? One can prove that. Given that that's true, that v over x and c over x are approach constant. So notice that x tending to zero means time tending to zero. You fix an r, let time tend to zero, you will get finite numbers here. So if lambda is greater than 1 and kappa is negative, you just read, of course, r of x just tends to a constant at x equal to 0. You get blow up. And you know immediately the rates. It's going to be r to the kappa for the density and r to 1 minus lambda for u and c. So that's how blow up can occur in these. And blow up, in all I say, is amplitude blow up, not gradient blow up. So that's the physical plan. Now, how do you actually solve? Of course, you have a similarity ansatz, and Euler gives you 3 coupled ODEs for these R, B, and C. It's a nice observation that goes all the way back to Gödel that R can be eliminated. So you have a system of 2 ODEs. And here you could get rid of the 1 over x by changing to a logarithmic scale. The ODEs are somewhat complicated, and they are, I'm not writing out what G and F are here. They are polynomials, and in some cases a rational function. But the D is troublesome because you divide by something that could possibly be 0. And where this D, the denominator, vanishes, those are called the critical lines. And in this setup, they are straight lines in the VC plane. Now, you can somehow try to cheat and get to, you don't have to worry about the D vanishing by dividing the 2 ODs, and you get the reduced similarity OD, which is, it only relates V and C along similarity solution. So I denote that by star. So you would analyze the phase portrait of this guy, and you would identify solutions. Say God gives you a solution to this. You substitute back into the V equation, and you solve that OD. Then this, so if the C of V solution you start with C hat, then this combined solution will then solve the VC system, the original VC system, this guy. And you can finally solve for R of x, but it turns out that's not necessary. There is actually an exact integral for R that determines R. So this is what makes the problem feasible to analyze, namely that you can reduce to a phase portrait analysis of this reduced OD. But let me go back. There are issues, right? You want really solutions of this original guy. So you have to be careful whenever you get close to a critical line. And you can cross the critical line in 2 ways, either by jump, which has to be allowed by the entropy conditions, and you would get an admissible shock, or you can cross at what is known as triple points, where all 3 functions, G, D, and F, they all vanish. And these triple points, they are present typically. It depends on the parameter values, but they are typically present. So I'm going to quickly go through the 3 main types of solutions we know about. So this is a somewhat busy picture, but what I've drawn is the physical plane, the RT plane, together with the phase plane, the VC plane. Now, I'll just quickly take you through how Göderle, or what the Göderle solutions of imploding shock looks like in these two pictures. So he starts with a quiescent fluid, and there is an incoming shock that propagates into that. The dotted line here is just a particle trajectory which just sits at still in the quiescent fluid until it gets hit by the shock. It gets dragged along by the shock, and there is a reflected shock coming out from the origin, and it gets dragged a little bit in the opposite direction outward. Now, to solve this in self-similar variables, it turns out that what you want to do is to start in the quiescent fluid. And unfortunately, you have to put the temperature to be zero there. This quiescent fluid is a cold gas. That means that you actually start at the origin in the VC plane, and you jump in an admissible fashion across the upper critical line. So these two straight lines are where the denominator in the ODs vanished, and you have to avoid them or cross at triple points. So you jump, you flow with you solve the ODEs until you get to a critical characteristic, which is the last characteristic that hits the shock. So this is a one characteristic. This is a one shock in Gödel's setup. So what that corresponds to in the VC plane is to cross at this, what is a triple point at C in this case. And you flow back to the origin. Now, why back to the origin? Because you, as mentioned earlier, you have to make sure that as x tends to zero, so t times to zero, you have to have v of x over x finite, and ditto for c over x. So as x tends to zero, you want finite quotients for v over x and c over x. You have to go back to the origin. So you flow back to the origin. It turns out that the origin is always, no matter what setup you use, it's a what do you call it, a star point for the OD. So any trajectories can come in along any straight direction at the origin. So many papers, many works on self-similar flow, they stop at time t. You have gotten blow up and you're happy or unhappy, I don't know. But Gödel actually went past that. He continued the solution down in the lower half plane. So it turns out that the upper half plane corresponds to negative times, the lower half plane to positive times. He continued down. You can show you have to arrive and leave the origin with the same slope. Otherwise, you get unphysical behavior. So what you can do is to continue through, and you can insert what is very natural. You expect this, that there will be a reflected shock, and that corresponds to, again, jumping across, but now the lower critical line to a certain trajectory in the lower half plane, and that's going to take you down to a critical point at infinity in the VC plane. So all this Gödel somehow did. Okay. One can discuss whether this is physical or not, and whether this is actually an example of blow-up, because in some sense, by having a cold gas at the interior in the quiescent fluid, the entropy is, I guess, negative infinity already. So strictly, one can discuss whether it's borderline physical or borderline unphysical, but at least it should be mentioned that that's a feature of this solution. About 20 years later, Hunter did a very similar type of analysis, but now for a physically very different case, namely where you have a vacuum on the inside. And it's not the shock that connects you to the fluid, but a particle path. And at this level of discussion, the only difference is that instead of starting at the origin in the VC plane and jumping across the critical line, now you have a smooth solution, but you have to start it from the intersection point of the two critical lines. This is point A, that's where the fluid starts. And you solve again, crossing through a critical line at the triple point and go to the origin. From there on, it is qualitatively exactly the same as in Gödel's solution. You can continue, jump, and go out. And this is an unsurprising thing that you would get a reflected shock because you have blow up in density, pressure, sound speed. So I should say that I forgot to mention that in Gödel's solution, at time of blow up, the density doesn't blow up. It's the speed, sound speed, and the pressure that blows up, but not the density. But in the vacuum case, the cavity case, all flow variables blow up. This was done by Hunter, assuming in his solution, this region of the flow before you hit the shock is isentropic. And I've recently worked on that you can extend this to non-isentropic vacuum flows of this type. Okay. And then much more recently, there has been a lot of activity on this. We can construct continuous and even smooth blow-ups. So this is a third type of self-similar blow-up where you don't have a vacuum, you don't have a quiescent region, but the fluid is in all of space and it's at positive pressure everywhere. So I worked with this on this with Kris Tsikou. And of course, but we only cared about continuous solutions. We didn't try to create smooth solutions. We just wanted existence of blow-up solutions. We were not even thinking of stability analysis of this. So the big result, of course, is Raphael Rodniansky and Scheftel. There is one thing I wanted to point out that, okay, so I don't care about smoothness, but what does the solution now look like in the phase plane? And with hindsight, it's very strange that this was not discovered much earlier. God knows there might be a paper out there having done that, but I didn't mention this, but the fact is that in the VC plane, the trajectories are symmetric about the v-axis. So you can simply take the picture in the upper half plane, flip it around to the lower half plane, and you have the correct phase portrait. Now, the lower part of this picture on the right here looks like Gödel or Hunter. And in particular, those solutions make use of a critical point at negative infinity. So in some sense, the only difference now is that to create these continuous and smooth solutions is that we'll make use of that also in the upper half plane. So you will flow down. So this is for negative times in the upper half plane. You will flow down through a particular trajectory. For a certain parameter regime, the triple point you're approaching is going to be a node, and you can continue in infinitely many ways. You can exit that in infinitely many ways. And what I've drawn here are two ways of continuing. Let's first look at the dotted guy. That's a very particular trajectory, namely the one that connects the triple point vertically to the origin. And you can prove that that's there under in a certain parameter regime. Now, that sounds interesting. Actually, what that means is that the particle trajectories look like the dotted ones here on the left in the physical plane, they stagnate. They have zero speed at time zero. The interesting thing is that if you now take the combination of this upper, which is a specific trajectory, together with this dotted vertical approach curve, and you can just reflect it about the v-axis, that's going to give you a complete trajectory. So you get the global in time, but continuous solution. There is no jump involved. You cross through here at least continuously, and you continue to the origin. And on below, you continue out exactly. It's a mirror image from the trajectory in the upper half plane. Okay, so you can perturb this because this is a node. There will be nearby trajectories that, for example, if you shoot down, you leave the triple point in a slightly to the left of the special dotted one, you will reach with an angle to the origin, continue through, and you will connect to the lower guy. What that means is that you will have created a solution with particle trajectories now stagnating along a certain curve given by a constant x. So this is the x where you cross the c-axis where v is 0, so that means speed is 0 along this curve. One surprising thing about these, so these are globally continuous solutions, but they blow up. Okay, this is in the lambda greater than 1 regime. And kappa is negative, so density, pressure, speed, sound speed, temperature all blow up. And yet your solution is continuous, which is surprising to me. I would have expected that if, say, pressure and density blows up at the origin, you would certainly create a shock. But that this picture tells you that that's not necessarily the case. Furthermore, you can set up the situation as with the thick line here, where the particle trajectories look like this. So at time of blow up, which is time 0, actually it's not that the fluid is rarefying and moving away from the origin, but they're all moving towards the origin, and yet no shock is generated. There is one more surprise in this picture, that for the dotted solution, so it's a very particular solution, and it only works for a certain parameter regime, or at least that's where I'm able to prove things, is that if you analyze the one characteristics in this flow, they will actually accumulate. So there is the density of one characteristics passing through the origin blows up. So this is there is accumulation of characteristics even, and still no shock develops. So this is a very particular case where we're showing that shock formation is not characterized by accumulation of characteristics or pileup of characteristics. However, for what I was in the title of this talk, the main point I want to make about all these three solutions of Gödeli, Hunter, and these more recent works, and I should also actually, this is a slightly too short version. I should have included the fourth one. Yesterday I learned about the work of Jenssen and a scholar and Vikal, where they produce a new type of smooth blow-up solutions. So there really should be a fourth case. What is common to them is that blow-up occurs, but in none of these solutions is there accumulation that the whole part or all of the fluid accumulates at the origin at a certain time. So for example, in these solutions, we could look at the the particle path in the Gödeli solution, a particle that is originally away from the origin stays away from the origin forever. Ditto in Hunter, and also here. You get close, but they bounce away. So there is no accumulation. Let me just, before we start on accumulation, let me just make a 1D remark. In 1D, yeah, I should have said that all of these blow-up solutions require dimension more than 1. You can try to find them in dimension 1, but the self-similar setup applies, but apparently it is not possible. I don't have a proof of this, but I've tried with Tsiku, and we tried quite a bit, but we were not able to find any case where the critical points line up so that you can actually build a global or even up to blow-up time self-similar solution in 1D. So that's actually an open problem for 1D planar symmetry Euler system. Can it blow up from bounded data? I'm writing it's sort of open because we'll later see an example that has something to say about this. But the main question I want to ask was, there were singularities. So in Gödeli solution and all the other solutions, at time of blowup, at least you're still working with L1 log functions. And you are specifically interested in if you can get accumulation, so direct delta in rho. Let's just get out of the way that there are trivial cases with a cold gas where this occurs. And if you put the temperature, you force the temperature to be 0, that means that the sound speed is going to drop out and your Euler system reduces to just pressureless Euler with a decoupled Burgers equation. So in this setup, the characteristics for the U equation are just particle trajectories, and it's immediate to generate accumulation. You could start with the initial velocity profile like this. This part will shock up. This part will rarefy. Everything moves to the left. And in the RT plane, these are particle trajectories. And you get accumulation. But this is kind of cheating. It's not really what what one is interested in. So non-trivial, actually, they are not that very non-trivial, but at least they are more non-trivial than cold gas accumulation flows. You can find such in affine flows, and I'll define that later what affine means. And these, as I mentioned, these are well known. They have been around at least in the 50s, since the 50s, and they were treated by Keller and Sedov in particular. Now, so if you want to do accumulation, it's reasonable to use a Lagrangian framework where you follow the particles. So in this, I will use, as Lagrangian variable, I'll use the initial position, y, and s will be its length. So a radial motion will now look like this. Y over s is just the unit radial vector. And r of ts is the radial position of particle s at time t. And that's what we want the equation of motion for. So if you prescribe an initial density profile and an initial pressure profile, this is the equation of motion, which is somewhat of a beast. And you want to simplify. And many people, this has been rediscovered many times, I believe. You can look for separated motions where the motion itself separates into a product of function of time, alpha, and function of your Lagrangian variable, f of s. And the affine motions is the particular case that f of s is just the identity. So the motion becomes quite transparent. So if you put this into your Euler flow, what it means is that the radial speed becomes a function which is linear in R. So they are called linear inner velocity models sometimes. And this has been studied by many people. It's also a fact that if you assume linear inner velocity, you have a separated flow. So they are actually the same thing. And this is much studied, McVitie, Keller, Sedov, and there is a whole bunch, a slew of Russian literature or Soviet literature that I'm not aware of in detail, but it's there. And more recently, Sideris has studied these in detail. Let me just mention that what Sideris does is that he looks at cases where this alpha is matrix valued. So he has instead of just doing spherically symmetric flow, you get ellipsoids, etc. And this has been analyzed by people, several Mahir, for example, in the audience. I don't know if this is a new observation, but it's a fact that if you look, you might think that, well, it's obvious, affine motions are particular cases of separated motions. But actually, these classes of motions are the same. If you give me a separated motion for some initial pressure and density profile, you can change, and in the smooth regime, you can change density and pressure profiles and make this into an affine flow. So it's not really, you can just as well just study affine flows. So if you make this of course is a very, very simplifying assumption. If you use this type of affine flow in the equation of motion, it separates, of course, it's a separated solution, and you get a simple ODE. And on this side, you don't even get an ODE. You just get the relation between the pressure and density fields, the initial density and pressure fields. In our setup, where S denotes the initial position, we must have alpha of 0 equal to 1. So alpha dot dot, the initial acceleration, so to speak, is given according to the ODE. Alpha dot dot the times 0 is lambda. So here the lambda is so this is different from the lambda in the self-similar solutions. I apologize. That's a separation constant, and the particular value 0 is special. It means that alpha dot dot must be 0. And P bar, the initial pressure profile, must then be constant from the equation of motion. So if lambda is different from 0, you fix lambda and alpha dot 0, and you solve your ODE. Assume that done. Now you fix a initial pressure profile, and you don't have a choice. The initial density profile to create such a solution we're looking at must be given in terms of the pressure. So it's a very constrained class, but it has lots of freedom. Yes, so you want positive pressure, so you don't, the sign of lambda and sign of the pressure gradient, they must be opposite in order to get a positive density. So before we look at actual solutions, if you fix your particle, it moves with radial velocity alpha dot times s and radial acceleration alpha dot dot times s. So at the initial time, these are respectively alpha dot times 0 times s. And as we observed later, this is a consequence of the ODE. The initial acceleration of your particle s is lambda s. So if we are looking at everywhere defined flows, meaning s takes all values up from 0 to infinity, so I'm not considering vacuum flows of this type. If alpha dot 0 is non-zero, you will have an unbounded velocity field in the far field as your particle is further and further from the origin. And if lambda is non-zero, you have an unbounded initial acceleration as you go out in the far field. So quite regardless of accumulation, these affine flows, they are singular already in this sense. of either unbounded initial velocity or unbounded initial acceleration. If both of these numbers are zero, it's easy to see you have a trivial quiescent state that's not interesting. Okay. So one of these things must happen. So cumulative flows of this type, of course, they correspond to a zero, a time at which alpha becomes zero. So I denote that by T critical TC. And if this occurs in this type of solutions, it's clear that the accumulation is total, that all particles reach are zero at time Tc. No matter what this is, if this factor vanishes, all the particles are at the origin. And it's well known, this was discussed in particular by Sedov and Keller, that this does occur in certain affine flows of an ideal polytropic gas. There are other types of accumulation that I'm not talking about here, but if you add self-gravitation, so there are many works, I'm just mentioning the recent one by Guo, Hadzic, and Yang. Of course, then you have an agent that helps you in accumulating mass at the center. And it turns out that for elastic bodies, there is a recent paper by Sidris where you also can get, without any self-gravitation, for an elastic body where you can get accumulation in finite time. So the affine flows comes in two flavors. Either lambda vanishes, and this means that you can assign any initial density you want, but the pressure you have to choose constant at time zero. And the resulting Euler flow looks like this. So if B here, which is the initial derivative of alpha, if that's negative, you see right away that you get the accumulation. All particles will flow along straight lines. In this case, all the flow is along straight lines. And the particle trajectories are simply S times 1 plus BT. The accumulation that happens in this type of solution is not surprising. Actually, none of them are, but in particular this one. What you are doing is that you start with a constant pressure, and you're sending the particles towards the origin with unbounded speed as you go to infinity. And you do it, it works out in that way that the pressure doesn't develop any gradient. At any fixed time, it's just a constant. So the pressure is irrelevant in this type of solution. It doesn't push or pull away, towards or away from the origin. The fluid particles just travel along straight lines. The further out they are, the faster they move towards the origin. So in some sense, in this case, the accumulation is a purely inertial effect. It doesn't have anything, the pressure doesn't play any role. And you can, by choosing different initial pressures, initial density profiles, you can create all kinds of behaviors. What I've drawn here are two examples. The thick lines are the particle trajectories, so they are straight lines in both pictures. And then I've drawn the one characteristics corresponding to two different choices of initial density. And you notice that, of course, by definition of one characteristics, they overtake particle trajectories as they move towards the origin. But you can arrange that either all of the one characteristics hit the center of motion strictly before time of collapse or accumulation, or they can actually shock up at the very time of accumulation themselves. So here in this lower case, there is accumulation both of particle paths and of one characteristics. Now, that was the case with lambda zero, in some sense, the simplest affine flows. if you choose lambda to be different from zero, so lambda is the separation constant, if that's non-zero, then your solution are now, instead of parameterized by density profile, they're parameterized by the initial pressure profile. And after a bit of work, you write out the explicit solution. So note again that U is linear in the radial variable R. And the density and the pressure are entirely given in terms of the pressure. And again, P bar prime, the pressure gradient, must have opposite sign of lambda in this case. So the bad case where accumulation can occur is when lambda is negative, so that means P bar prime is positive. That is, the pressure gradient is positive, the pressure is larger the further away from the origin you are. And you can set up different situations. If you send the gas away from the origin sufficiently fast at time zero, then no accumulation occurs, and the pressure gradient that tried to push you towards the center of motion loses. But if it's weak expansion in the original fluid or initial convergence of the fluid, then accumulation does happen and pressure wins. So in this case, you could say that the accumulation is completely different. Now it's purely due to adverse pressure gradient. So this is pressure gradient driven. And you can create lots of solutions to your heart's content. Let's quickly go through one example. It turns out that the ODEs simplify very much when n and gamma multiply out to 2 in this fashion, which means in 1, 2, or 3 space dimensions, gamma should be 3, 2, or 5/3. And you can solve the ODE for the motion, and you see right away that this will vanish at the critical time. So all particles, no matter what value S has, all accumulation happens at this time. Now, in order to, and so this is particular about this affine solutions, that you can solve for the motion regardless what the initial pressure constant was, pressure profile was. But if you make a choice, now you can calculate the one characteristics also, and they look very similar. The only difference is that you have a different exponent. So again, in this case, all the one characteristics together with all the particle trajectories will accumulate at the origin at time of collapse. And a particle, if you look at the track of a particle, it's overtaken by all one characteristics that start further out. So the picture is like this. Again, the solid line is a particle trajectories. The one characteristics, all of them will hit before time zero, before TC. There is a last case where if you start with the positive lambda, so that the pressure gradient must be negative, so now the pressure decreases the further out you are, then and this is perfectly reasonable, that no accumulation now happens. The pressure wins no matter what. Even if you try to send the gas very quickly towards the center of motion, the pressure wins and pushes it away. Still, in these solutions that are global in time, the far field behavior of the velocity field in particular is singular. As we saw, the velocity grows linearly at infinity. Now, I'll just make one observation, that these affine solutions, the space dimension is not important. They happen in all dimensions, 1, 2, 3. So if you combine these two facts, you get an illustration of something that I think is an interesting thing about Glim's existence theorem in 1D. So now let's look at the 1D situation, but for these affine type solutions. So here is an example where you can create instantaneous blow-up. Maybe I should put that in quotation marks, but of small BV solutions in 1D. And this comes about as follows. So we fix a lambda positive. Okay, so the pressure must decrease away from the origin. We choose alpha dot of 0 to be 0. That means that the fluid initially is going to be at rest. And then for the pressure profile, you choose a Gaussian. So this decreases as it should because lambda is positive. So the gas starts from rest, and this particular pressure gives you also an initial Gaussian for the density. So the temperature in these data is actually constant, strictly positive and constant. It also turns out that alpha dot of t is a bounded function of time, and alpha itself is always greater or equal to 1. That just means that particles are moving away from the origin. So what I've written down here is the resulting flow, not the flow variables, but the conserved variables, rho, rho u, and energy. And they take the following form, and I'll repeat them here. So the conserved quantities look as follows. They all have exponential or Gaussian on them, and they are all multiplied with I should have mentioned it. The initial pressure, you throw in the parameter P naught, so strictly positive, but it's at your choice what it should be. And all of the conserved variables inherit one factor of P naught. So if you fix lambda and you choose and you create your solution and you now fix P naught very small, you get small BV data. And you get, as you should, according to Glimm's theorem, you get a global in time small BV solution. The variation remains small, and you remain small in L1 on all of space. And but this is an affine solution. So the velocity field is unbounded. It's linear in R. So alpha of t is strictly by nothing funny happens with the time factor. You fix time, you have an unbounded speed for all times positive. So the observation I wanted to make is the following, that Glimm's theorem is true, that the conserved variables remain small in BV. But for us, a physically relevant quantity like the velocity can well blow up immediately. So I thought that was an interesting observation that having worked on 1D problems, I should have known about years ago, but this was news to me. You might wonder if this, so remember that the initial density profile decays like exponentially, like a Gaussian. And you might wonder that, oh, that's approach to vacuum, and Euler at vacuum is fishy. Well, not really in this case. This is the full order system. So the eigenvalues in these data at time 0 are not degenerate. Okay, so the initial characteristic speeds are 0 and plus minus a strictly positive constant. So this example, at time 0, you are uniformly within the regime of strictly hyperbolic system. So Glimm really does apply in this case. Okay, so that was the 1D case. I should summarize. The self-similar flows exhibit amplitude blow-up, but not accumulation. But affine flows, you can create accumulation. But they all suffer from unbounded far field velocity. And I didn't mention that, but they also have infinite energy. These are infinite energy solutions. You might think that that's because of the unbounded velocity field, but that's not necessarily the case. It's the internal energy, that the total internal energy is infinite by by necessity. And this is a somewhat unsatisfactory situation. One could try to build other non-affine Euler flows, and I can do that in 1D. So the cumulative flows that do exhibit accumulation. But again, I'm not able to get rid of the unbounded velocity field. So that's what's missing. If anyone can find the cumulative flow with the bounded velocity field, that would be very interesting. Just a couple of remarks that I don't see how it's possible to take one of the affine flows that do exhibit accumulation and adjust it or perturb, modify it in the far field in order to get a bounded velocity field and still produce accumulation. It seems to me that whatever you do is going to destroy accumulation. So that's maybe a sign of health, a healthy sign of the Euler system, but the question remains very much open. Another thing, another reason to be critical about the accumulation solutions from affine flows is that they work in any space dimension. I would expect that if one can create a cumulative flow for Euler, it physical in the sense of having a bounded velocity field, it would have to be done through wave focusing in multidimension, but that's just a guess. And on that happy note, I'm done.